In this video, let's take a look at the remainder theorem and the factor theorem regarding the division of polynomials. The division of polynomials is an important topic in algebra, because if the remainder of the division is 0, like in this example, then from the division algorithm, we can factorize the polynomial like this. In other words, for polynomials with higher degrees like degree 3 or degree 4, if we can find a divisor of which the remainder is 0, then we can factorize this higher degree polynomial by the long division. However, finding such a divisor may be problematic, because to check whether the remainder of the division is 0, each time we need to do this time-consuming long division. So we are interested in this question. Can we obtain the remainder of the division without performing the long division? The answer is yes, if the divisor is a degree 1 polynomial like in this case. Let's take a look at this situation. Suppose the divisor is x minus 2, so it is a degree 1 polynomial. We let the dividend be fx, the quotient be qx, and the remainder be rx. These functions, fx, qx, and rx are polynomials. We have learned that the degree of the remainder should be less than the degree of the divisor. In this way, because the divisor is degree 1, so the remainder must be degree 0. In other words, the remainder must be a constant, so we can simply denote it by r instead of rx. By the division algorithm, we can then obtain a formula of fx like this. Now let's see what will happen if we input the value 2 in the function fx. We can see that f2 is equal to 0 times q2 plus r. Although we may not know the value of q2, since we have 0 here, q2 is eliminated, and therefore we can get that f2 is equal to r. This is a powerful result. That means if fx is given, then we can find the remainder of this division by simply computing the value of f2. This is how we can obtain the remainder of the division without performing the long division. Generally, by a similar argument, we can conclude that when a polynomial fx is divided by x minus a, then the remainder is simply fa. This result is known as the remainder theorem. More generally, when a polynomial fx is divided by mx minus n, then the remainder is fn over m. To obtain this input value for the remainder, we just need to consider the value of x to make the divisor equal to 0. In other words, when mx minus n is equal to 0, we can get that x is equal to n over m. And then we know that fn over m is the remainder when fx is divided by mx minus n. After understanding what the remainder theorem can do, the factor theorem is a natural result from it. Suppose we know that fx is a polynomial and fa is equal to 0, then that means the remainder when fx is divided by x minus a is 0. So we know that fx is divisible by x minus a, and hence x minus a is a factor of fx. More generally, if we know that fx is a polynomial and fn over m is equal to 0, then we can conclude that mx minus n is a factor of fx, and this result is known as the factor theorem. Now let's take a look at a few examples and see how we can apply the remainder theorem and the factor theorem. In this example, it is given that when x squared plus kx minus 2 is divided by x minus 3, the remainder is 10. Now we need to find the value of k. Before we learn the remainder theorem, we need to perform the long division to answer this question like this. Now with the remainder theorem, we know that to find the remainder for the divisor x minus 3, we just need to input the value 3 in the dividend like this. Therefore, we know that this expression is equal to 10. As a result, we can solve that k is equal to 1. With the remainder theorem, we can solve this kind of problems involving the remainder of the division without referring to the long division. Next, let's take a look at this example. Suppose fx is equal to 2x squared plus ax plus b. When fx is divided by x plus 1, the remainder is minus 2. And when fx is divided by 2x minus 1, the remainder is 1. Now we need to find the values of a and b. According to the remainder theorem, the remainder when fx is divided by x plus 1 is just f minus 1. And the remainder when fx is divided by 2x minus 1 is just f1 over 2. So now we can set up two equations in a and b and then solve for them. As a result, we can get that a is equal to 3 and b is equal to minus 1. Afterwards, let's take a look at this example. It is given that fx is equal to x cubed minus 6x squared plus 11x minus 6. In part A, we need to show that x minus 2 is a factor of fx. According to the factor theorem that we have learned, if fa is equal to 0, then x minus a is a factor of fx. That means in this case, we should check whether f2 is equal to 0. After calculating the value of f2, we can see that f2 is really equal to 0. So we can conclude that x minus 2 is a factor of fx according to the factor theorem. And then in part B, we need to factorize fx. By A, we already know that x minus 2 is a factor of fx. So by performing the long division with fx as the dividend and x minus 2 as the divisor, the quotient obtained here is another factor of this polynomial fx. By the division algorithm, we can conclude that fx is equal to x minus 2 times x squared minus 4x plus 3. In this way, we have successfully taken out the factor x minus 2 from fx. For the factor x squared minus 4x plus 3 here, it can be further factorized by the factor method. As a result, fx can be completely factorized as x minus 2 times x minus 3 times x minus 1. Finally, let's take a look at this example. It is given that 2x plus 3 is a factor of fx and fx is equal to 2x cubed plus x squared plus kx minus 9. In part A, we need to find the value of k. Because we know that 2x plus 3 is a factor of fx, so the remainder when fx is divided by 2x plus 3 is equal to 0. From the remainder theorem, we should know that f minus 3 over 2 is equal to 0. Strictly speaking, this is a result from the converse of the factor theorem. As a result, we can solve that k is equal to minus 9. Afterwards, in part B, just like the previous example, we can perform the long division with fx as the dividend and 2x plus 3 as the divisor. The quotient obtained is another factor of fx. Hence, by the division algorithm, we can conclude that fx is equal to 2x plus 3 times x squared minus x minus 3. In this case, the factor x squared minus x minus 3 cannot be further factorized. So this is the final answer of this factorization. To conclude, the remainder theorem helps us to obtain the remainder directly without the long division. But it only works when the divisor is a degree 1 polynomial. For the factor theorem, it is a natural result from the remainder theorem. Basically, it means that if the remainder is 0, then the divisor is a factor of the dividend. By applying the factor theorem, we can obtain a factor of a polynomial, and hence we can factorize it by performing the long division.